So today we are going to kind of wrap up Unit 6. So we've done a lot with the trig functions over the past several weeks. We've studied how to get them. We've studied their parent graphs, their transformations. So what we're doing now is we are going to look at real-life applications of trig functions. Excuse me, and how their characteristics can be interpreted when we put them into equations and graphs. So this is a shortened version of what is in your workbook in lesson 35.1. So it says, Tyrell is an engineer at Rocket Rides. His job is to design amusement park rides that meet the needs of the company's client. A new client asked Rocket Rides to design a Ferris wheel with the following constraints. So remember we talked about constraints earlier in the year, and those are just restrictions, characteristics that have to be met. So the first is that the diameter of the wheel has to be 88 feet. So remember that diameter is twice the radius. It says the highest point of the wheel must be 100 feet above the ground. All right, so they're going to take that into consideration. And then finally, the wheel must make one full rotation every 60 seconds. So wherever you start, you're going to come back to that point 60 seconds later. So based upon this information, Tyrell creates a sketch for the ride called the Sky Wheel. So they're calling their Ferris wheel the Sky Wheel. And here's our sketch. So notice the constraints that are met from point B to point D. That's the diameter of the wheel, so that's labeled 88 feet. Then it says that the highest point has to be 100 feet off the ground. So if this is the ground, this line right down here, then it's 100 feet from that line to the top of the wheel, which is labeled at point B. So that meets the parameters that were discussed for what the client needs. So it says Tyrell wants to write a function that models the motion of the Ferris wheel. He starts by considering the motion of a car that begins at point A. So point A is right here. So we're essentially sitting in this car and we're considering the motion starting there. We probably are starting there to be nice because that's where 0 is on the unit circle, so that helps our life a little bit to start at that position. So first question that you have to answer is, what is the height of a car when it is at point A? And then explain. All right, so I am going to leave some awkward silence in here because you need to actually think through that. You can talk about it in your group if you want, but go ahead and determine what is the height of the car. So essentially right here, you need to determine what that height is and explain your answer. So take a couple minutes in your group to go ahead and do that. Right, it's been a little over a minute. I don't know if that's quite enough time because I can't see your papers. So if you need more time, you can pause the video for a second. But if not, we're going to go ahead and move on. So the height of the car when it is at point A, hopefully you figured out that if this entire length is 100 and the diameter is 88, if you take 100 and subtract 88, you get 12, which means that the bottom of the Ferris wheel is actually 12 feet off the ground, which means that this height here to point A is going to be that 12 plus the radius of the circle. If the diameter is 88, the radius is 44. So 44 plus 12 gives you a total of 56. So hopefully you came up with 56 feet. For the explanation, we can say the wheel is 12 feet off the ground. Plus 44 feet to the center, which again is the radius of the circle. All right, so the height of the car when it is at point A is going to be 56 feet. All right, so now in step 2, we're going to make a table showing the height of the car in feet when it's starting at point A and rotates counterclockwise. So notice they've got an arrow here indicating that we're rotating in that direction, so counterclockwise. So when time is 0, that means that's when you're before the ride starts going. So that one is going to be at 56 feet. Remember that the Ferris wheel makes one full rotation every 60 seconds. So that means that when we get to 60 seconds, we should be back where we started at 56 feet. Again, I'm going to give you a couple minutes to go ahead and figure out and fill in the rest of this table within your group. All right, again, if you need a little more time, you can go ahead and pause the video if you don't have your table quite filled out yet, because I can't see, I don't know how much time you need. So we're at 56 feet at 0 seconds. If every full rotation is 60 seconds, that means moving from one point to the next labeled point is going to be 15 seconds because we got 15, 30, 45, 60 seconds. So 15 seconds in, we would be at point B. The height of point B, because it's the top point, is going to be 100. At 30 seconds, we would rotate to point C, which is on the same line as point A, which is 56 feet above the ground. At 45 seconds, we're down at point D, which you can see with my little mark here is 12 feet off the ground. So once we've got that, then again at 60 seconds we're back to point A, it's at 56, and then we're going to repeat because we're keeping on rotating. So 75 seconds would be point B again, which is 100. 90 seconds would be point C, which is 56. 105 seconds would be back to point D, which is 12. And then 120 seconds, because it's a multiple of 60, you'd be back at A, which is 56. Okay, so this table essentially becomes a T-chart, And what I have done with that over here at the right is created a graph. So time on my horizontal axis and height on my vertical axis. So 0, 56, 15, 100, 30, 56, 45, 12, so on and so forth. You can see that each of those dots represents one of those points in the table, and that we've created a graph from that. So question number 3, is this function periodic, and explain. So again, go ahead and take a minute to answer that question and explain your answer. All right, that shouldn't have taken as long as the other ones, so hopefully you've got that answered. Yes, this is periodic. This is what we did in section 34.1 when we looked, and we said that the values repeat at regular intervals. So yes, this is periodic. What is the amplitude? So take a look at this graph, and remember that these values are at 56, these values down here are at 12, and these values here are at 100. So that may help you if you forgot where they were on the graph. So go ahead and fill out what your amplitude is. Hopefully you haven't forgotten how to calculate amplitude. Amplitude, remember, is the distance from the midline to the maximum, or it could also be considered half of the height. So the entire height is from 12 to 100, which is 88 feet. So half of that is 44. So 44 is the amplitude here. Number 5, what is the period? Remember that period is the horizontal length of one full cycle. Remember that we drew boxes, rectangles around our graphs in order to determine the period. So go ahead, draw a box around one full cycle of this graph in order to determine what the period is, and then record it on your paper. Hopefully you drew your rectangle looking something like that. And remember, it's the horizontal length of that rectangle. So the period is 60 seconds. Amplitude was obviously in feet. What is the equation of its midline? I've kind of already answered that one for you, so I'm not going to give you time to do that because it should be obvious. I already labeled it here. The midline is this row of points, which is at 56 according to our table. So remember, when we write an equation, needs to have y equals, because it's a horizontal line. So y equals 56 is going to be our midline. Which parent graph shape does this function have? So we've studied 3, sine, cosine, tangent. Which one is this? Go ahead and write it down. Hopefully you answered sine, because this starts at the midline. You know it's not tangent because it doesn't have the asymptotes and branches to infinity. So you knew it was sine or cosine. Since this starts at the midline, you should have answered sine. So now that we know that it's a sine curve, number 8 asks us to use the period to find the value of b. Remember that the formula for finding b and or period in a sine or cosine graph is 2 pi divided by b equals the period. So in this case, the period is 60. So 2 pi divided by b equals 60. So if we solve this for b, we end up with b equals 2 pi divided by 60, which reduces to pi over 30. So the value of b is pi over 30 in this case. All right, so now that we've done that, number 9 asks us to compile the information above to write a function to model the motion of the sky wheel in the form h of t equals a sine b t minus h plus k. So we've had a lot of practice looking at a picture and writing the equation. So this is no different than what you did on your worksheets last week. So we look at this picture. We know it's a sine curve, so A stands for amplitude. So we already know the amplitude. We recorded it, so that's going to be 44. Sine. We just solved for B, so we can go ahead and plug that in. Pi over 30. H would be horizontal shift, meaning how far left or right did we move to start our graph? Well, our graph started on the midline, so we didn't move left or right any at all, which means H equals 0, which means we don't need to write it. So we can just write the T right next to the B instead of doing a minus H, because H is 0. Then finally, plus K. Remember, K represents your vertical shift. So how far up is your midline? And in this case, the midline is at 56. So that's what we're going to write here. All right, almost there. Determine a reasonable domain and range for h of t. So when it says reasonable, remember that that means something that makes sense for the real life situation. So we can't just say, oh, domain, it's a sine curve, so it's all real numbers. Because remember that the domain here represents seconds. So we have to think about what makes sense for the real life situation. So since this is time, we know that time can't be negative. So when we go to write our reasonable domain, we would say that t, because that's our variable here for domain, has to be greater than or equal to 0, because you can't have negative time. So that's a reasonable domain and domain. The range are our vertical values. In this case, our variable is h of t, and our y values or vertical values go between 12 and 100. So between 12 and 100 is our reasonable range for this function. Last but not least, bringing it all together, and this is extremely important. Describe the real life meaning of each of the important characteristics of the trig function. Got to move my recording space down so you can actually see what we write. So this means, like, let's relate it back to the real life parts. So if we look at the amplitude and what that was in the real life situation, the amplitude, the 44, was also the radius of the circle. So when it tells you a wheel, a tire, anything that takes circular motion, when it tells you or implies that the radius is a certain value, that is telling you the amplitude of the equation. Also, notice that the period, 60 seconds, that relates back to this. It's how long it takes to make one full rotation. So the period is the time for one full rotation. There could be other real life situations where it's not necessarily a rotation, but maybe a cycle. So that translated into the period of our function. Look also that our k value was the height of the center of the wheel. So K was the center height of the circle. So how far the center of the circle was off the ground. That was our K value. This is all really, really important, because not only is it important because it makes the connection to real life, but it's extremely important on your embedded assessment, because your embedded assessment, when you look at it, totally tires. Everything is related to a real life tire situation. So it's really imperative that you know that the amplitude is the radius of the circle, that the period is the time it takes for one full rotation, that K is the center height of the circle, and that you can see that you can figure out how to graph and how to come up with a picture of the cycle based on making a T-chart. So all of this lesson is extremely important for that embedded assessment. This in and of itself is like a review for your embedded assessment. So if you need to watch it again, the link is going to be on the website, but hopefully that all makes sense. And that is all for today.